Now I want to explain an article which uses unsupervised entity learning. I mean, most of the articles in entity linking literature is about using deep learning things, but this paper in particular in 2021 uses a totally different and very, very simple, super simple approach for entity linking. First of all, it is unsupervised, and then the idea is that it uses low-rank subspace. It creates low-rank subspaces. But the problem of this article is that, and it is mentioned in the article, is that you should have a great knowledge graph so that you can create a good embedding. If your knowledge graph is not great, then this doesn't work. And these are positive samples that it's about entity linking, other interesting papers that I will explain. The motivation is that the entity linking is an important problem with many applications. Most previous solutions were designed for settings where annotated training data is available, which is, however, not the case in numerous domains. So the idea is that they propose a lightweight and scalable entity linking method, eigenthemes, that relies solely on the availability of entity names and a referent knowledge base, which is a big hard assumption, as I said in the previous slide. Eigenthemes exploits the fact that the entities that are truly mentioned in a document, we call them gold entities, tend to form a semantically dense subset of a set of candidate space. So we create a subspace, and those gold lie on that. So geometrically speaking, when representing entities as vectors or some given embedding, the gold entities tend to lie in a low-rank subspace of the full embedding space. Eigenthemes identifies this subspace using singular value decomposition and scores candidate entities according to their proximity to the subspace. So this is the low-rank subspace. As you see, the gold entities lie on that. So there are many things, but you see, science and Michael Jordan computer science go together. They lie in the same subspace. So they employ a simple and efficient approach to generate candidates, which is similar to design of candidate generator given by Titov. Given a mention, the entities that contain all the words from M are considered candidate entities. So for any mention, we have some candidate entities, E1, E2, we rank them. And for example, Michael Jordan, the basketball player, if it is and this one are candidates. So this one and this one correspond to two different entities. Since the degree of an entity roughly captures its popularity, the candidate entities are sorted based on the degree of their corresponding vertices in the undirected version of Wikidata knowledge graph. What are eigenthemes? Given a document with a number of mentions, each mention with a set of candidate entities that it can be linked to, and vector representation for all these candidate entities, eigenthemes builds a matrix of a vector representation of all candidate entities within the document and uses singular value decomposition to learn a subspace spanned by a number of components referred to eigenthemes. So we have K. This is just a hyperparameter. So we have K eigenvectors. And so our E is just a d-dimensional embedding for the entities. So given a document D, we build a candidate space. So this is candidate space by taking the union of the candidate entities. So we have the n of number of document times, and as I said, the dimension is d dimension. So this is the document embedding matrix E of d. So for each document, we have this E sub d, which is document embedding. So to learn subspace, so for each document, we have a subspace. For example, for document D, we have subspace D that lies some entities on that. And we use a singular value decomposition that in machine learning, we use that a lot. As SVD of E of D, the sub decomposes each entity embedding in a matrix as a linear combination of left and right singular vectors. So they approximated. Instead of E sub D, which is huge, we have a lower rank approximation where U sub K are the left singular vector and V sub K is the right. And this sigma, this diagonal and has K larger singular values. So as I said, this is a low rank approximation of your original matrix that has rank K. And as I said, K is a hyperparameter. So here we have just K eigenvectors. And so incorporating weights as a prior likelihood, because we know some prior knowledge, so then we can just multiply with that, and then we have a better likelihood. And for similarity function, we just project it. So for a mention M, E sub M is just the embedding of entity EM in sub M. And we project it to that space that we have. This is a space, and this is the entity that we want. So for each entity, we have the score of that. Very simple. So we didn't do any deep learning things. Everything is straightforward and very fast. But as I said, it needs a very great and excellent knowledge graph, which is in reality, even if you look at the biomedical thing, ontology, and those things, they are not perfect, and the lexical similarities are not always the case, because two words could have even zero similarity, in terms of lexical, word by word, in alphabetical form. So it's not natural.